Hey everyone, today we're going to be starting another math lesson, still continuing with our trigonometry unit. I hope the glare from this light won't get in the way too much. I'm going to try to be careful of that. I've moved into my dorm, so I'm trying to figure out a new setup now for the rest of these lessons. So hopefully this works. Hopefully you guys can see the board. We've got new markers and everything, so hopefully this works. Today we're going to be talking about two things. The first part is going to be on trigonometric identities. Now we haven't talked about this before, so this is completely new. There's only a couple of things that we really need to talk about, and the concept itself isn't that difficult. The whole purpose of trigonometric identities is to make your life easier when you're doing problems that involve trigonometry. Okay, so the first part of it is going to be trigonometric identities, and then the second half is going to lead into what we're doing next. Okay, and the thing that we're doing next, well, the thing that we do next is going to involve a little quiz, which I think I gave you guys a bit of a heads up on. But so we're going to start with trigonometric identities. If you go on Google and you type in trig identities, you're going to get lots of stuff. There's lots of different identities out there. There's lots of different types of identities out there, and you can use them in a variety of circumstances. We're only going to talk about two. They're two of the simplest, maybe not the complete simplest, but two of kind of, if you know 5 trigonometric identities because you just started learning, you will know these two. So these are at the very, very beginning of any discussion, any introductory discussion on trigonometric identities. So basically the way it works is these are equations that use the trigonometric functions or rules or whatever that we've talked about so far with sine and cosine and tangent, and they create these equations that you can use. It's a calculation somebody's done that, multiplying two different trigonometric functions together gives you one result, and multiplying two different ones, or adding or subtracting or squaring, your answer to sine of theta, you square it, sine of 30 degrees squared gives you some number that maybe you could work with in your question. So things like that it's an equation, somebody's done the calculation, that if you have the necessary information, it spits out an easier way to express your answer. Or maybe it's a vital step sometimes in proving one thing equals another or doesn't equal another. So we're not going to be proving a bunch of stuff. I just want to show you these identities, and then it can possibly make your life simpler in the future. So the first one, we're actually going to derive both of these identities, and what that means is we're going to start without the equation. We're going to start with something else, and we're going to create the equation ourselves. Okay? So what we're going to start with is a triangle. Okay? Simple enough, and it's going to be a right triangle. Okay? Now, we already know how sine and cosine and tangent work, so if I put an angle theta over here in this corner, then you know that this side over here is the opposite side. You know this side down here is the adjacent side, and this side up here is the hypotenuse. This one doesn't change regardless of which angle you're interested in, because we have a right triangle, so the hypotenuse is always across from the right angle. Now, what I'm going to do is I'm going to change these names. I'm not going to make them complicated. I'm just going to give them different names according to something else that we've talked about. I'm going to call them A, B, and C. So I'm going to call the opposite side A, I'm going to call this adjacent side down here B, and I'm going to call the hypotenuse C. Okay, so this is what we have. We've got A being the opposite side to theta, B being down here, the adjacent side, and C being the hypotenuse. So if you wanted to, you could express sine theta in terms of these things, right? We could say sine theta is, well, we know sine is normally the opposite. We know it's normally the opposite side over the hypotenuse, but we don't have those names anymore. We just know that the opposite side is this one over here. So instead of saying opposite over hypotenuse, we say sine theta equals A over, and we know the hypotenuse is C right here. So sine theta is A over C. Okay, that's if theta is this angle down here. So we've got sine theta is A over C, opposite over hypotenuse. Okay, now we could do the same thing for cosine. Cosine of theta is B over C. This is the adjacent side. If you remember, cosine is adjacent over hypotenuse. So the adjacent side down here is B, and then the hypotenuse, once again, is C. So we put that there. And lastly, we can do the same thing for tangent, and we get tan theta. Well, we know tangent is opposite over adjacent, so we get A over B. Okay? There we go. So this, we already know, but this is not any new information. This is just going to be important a little bit later. Okay? So this is, with the triangle that we've drawn, this is the information that we have. All right? We know that sine theta is A over C, cosine theta is B over C, and tangent theta is A over B. All right, now I'm going to move the triangle out of the way. I'll draw a tiny version of it up here. But as long as you have it in your books once, and that's fine. You don't need it multiple times. And I'm going to get rid of it here so I can use this space to work. Now, we talked about something called the Pythagorean Theorem. Hopefully you remember this. That's basically, it's a rule for any right angle triangle where the hypotenuse, that is side C, squared, so the length of the hypotenuse squared is equal to the length of the other two sides squared and added together. So square A, square B, and add them together. A squared plus B squared equals C squared. All right, hopefully that light's not in the way. I'm not very good at this. So we've got A squared plus B squared equals C squared. That's the Pythagorean theorem. We already know that. But what if, just for fun, why not, I will divide everything here, every single term, I'm going to divide it by C squared. Okay, you're going to see why in a minute. So it doesn't make sense why I'm doing this until you get to the answer and you realize that the answers might simplify your life in the future, depending on the problem that you're working on. Okay, so I've divided everything by C squared. Now, C squared divided by C squared, that's just dividing something by itself. So this whole thing is going to cancel out and give us 1. Okay? But now over here we've got A squared divided by C squared. Well, that's actually the same thing as A times A over C times C, right? But I could also write that as, if I've got A over C, C, I could say, instead of doing A times A divided by C times C, I could do A divided by C times A divided by C. All right, I haven't changed anything because multiplication of fractions still means I'm going to do A times A. That'll give me my A squared. C times C on the bottom, that'll give me my C squared. So I haven't done anything wrong by, I'm just going to write that a little bit neater, by doing A over C times A over C, right? But if I've written A over C and I'm multiplying it by itself, then, well, I don't need to write it twice. I can just write A over C squared. All right, now you can make this an extra step in your book. You can write A over C times A over C, and then in the next line put A over C squared. I'm just doing it here because I have limited space and don't want to spend so much time erasing. So we've got A squared over C squared is the same thing as A over C all squared, okay? So I can put the fraction inside and then just put one exponent, one little 2, out there. And I can do the same thing for b squared over c squared. So I can do a over c all squared plus b over c all squared. Now if you notice, this is all well and good, but I still have just a bunch of letter names. But now if you look over here, we know what a over c is. A over c is just sine of theta. And similarly, b over c is just cosine of theta. So I can actually write 1 equals sine theta squared plus cosine theta squared. Okay, so that's based on, we've gotten from a squared over c squared became a over c all squared, but a over c is sine theta. So instead of writing a over c in the brackets, I've just written sine theta in the brackets, but it's still squared because the fraction a over c was squared. And then same for b over c. I've subbed out b over c. I don't want to write the fraction, so I write cosine of theta instead. All right? And what this lets me do, this gives me our first trigonometric identity, which is sine squared theta. This is basically, this notation down here means the same thing as sine theta squared. So this means sine theta multiplied by sine theta. I'm going to write it maybe the less confusing way, just so that you don't forget what this means. So sine theta squared plus cosine theta squared equals 1. And that is a trigonometric identity that you can use if, for instance, you're not given any information about what you're working with. You're not given any information, let's say you're working with a triangle, and I tell you what sine theta is, and I don't tell you anything else. Then you can actually use this equation to figure out what cosine of theta is. Let's say if that was the question, if I give you sine theta and I ask you to tell me, well, what's cosine theta, then you could use this equation to figure it out. Okay, so hopefully that makes sense. This is our first trigonometric identity. The second one is also quite simple. So I'm going to get rid of this. It's still working with the same triangle, so I'm going to leave all the stuff on the left. And we're just going to think about it in a different way. We're not using the Pythagorean theorem this time. So you're not going to, I can't explain why I'm starting with what I'm starting, but I can show you what answer it gives you. So I can't describe the reason I'm starting where I am for this bit is because I know what the answer is. Okay? So let's take sine theta, which is just some number, right? It's the ratio of the length of this side and the length of the hypotenuse. So it's just some number. And I can divide this by another number, let's say cosine of theta. Okay? Sine theta divided by cosine of theta. This is allowed mathematically because this is just some number on top. This is just some number on the bottom. You can multiply and divide whole numbers, decimals, negative numbers. The only thing that you can't have is a 0 on the bottom. Anything else works when you're working with fractions. All right, so the only thing we can't have is a theta value that makes the cosine of theta 0. We'll get into that later. But basically, this equation, I haven't done anything criminally wrong by writing sine theta divided by cosine of theta. But now I want to know, what is this equal to? All right, now I could write this slightly differently. I could write this as sine theta times 1 over cosine of theta, because this is basically sine theta over 1, and then I'm just multiplying fractions. You multiply the tops together. Sine theta times 1 is sine theta, 1 times cosine theta is cosine theta, so I haven't done anything wrong. Now, if we look over here, sine theta is a divided by c, right? We already knew that. A over c times 1 over cosine theta. Cosine theta is b over c. But I don't like this because now I have a fraction in the denominator. And it turns out what I can do is basically, if I'm dividing by this fraction, I can just flip the fraction. So instead of having it as b over c, I can make it c over b, and then move it up to the top. So basically I can write it as a over c times c over b is basically what I'm allowed to do here. Okay? Now if I have this much, a over c times c over b, I'm basically doing a times c divided by c times b, right? But if I'm multiplying by c and then dividing by c, I could just cancel out the c and save myself time. So I get rid of those, and that leaves me with, if I just move over here, that leaves me with just a over b, right? I had a times c divided by c over here, and then the b, we're not worrying about the b. But if I'm multiplying by c and dividing by c, I can just cancel those out, and that leaves me with a divided by b. But the thing is, a divided by b is tan theta. And so what that tells you is that if you know the sine and the cosine values of a given angle theta, then you actually also know tan theta. You can use it to calculate tan theta. All right, so this is our second trigonometric identity. I'm probably not going to give you any exam questions where you need to use a trigonometric identity. I just thought this is something that you should see for anyone who's interested in pursuing math in the future. These kinds of things are really handy to know before you enter university or advanced high school math. So this video is getting a little bit long, but I'm going to stop it there, and in the next part we're going to pick up with the unit circle. That's the next thing we're going to talk about. Alright, so if you have any questions, leave a comment. Otherwise, I will see you in our unit circle lesson.